So let's turn our attention to another sort of non-ideal quality. So we said that for our two transistor current source to work, Q1 and Q2 have to be matched transistors. And we said that means that the beta is the same, the temperature is the same, the leakage is the same, and so on. And so we said typically that's not going to be an issue if they're fabricated close enough together on the same integrated circuit. However, we can have mismatched transistors, and we're going to see we can actually use this to our advantage in certain cases. So let's go back to our more general equations, and let's say that our I naught, which is our IC2, is equal to some reverse saturation current, IS2, times the exponential of VBE divided by VT. And so as we said in a previous video, our VT is our thermal voltage, which is related to our temperature. So VT is our thermal voltage, which is equal to KT over Q. And so we're not going to be too concerned with that exact value. We just need to keep in mind that that is dependent on our temperature. And our IS2 is our reverse saturation current. Okay, and so we can do a similar thing with our transistor Q1 that's on the left side of that two transistor current source. And we can say that our reference current, Iref, is approximately equal to IC1. And so that's using the same argument that we had talked about in a previous video, where we basically said we're going to neglect our base currents, IB1 and IB2, because we know that beta is much greater than 1. So essentially our collector current is so big that our base currents are almost negligible. And so that's going to make our math a little cleaner for this first order approximation. So we know that that collector current I1 is equal to IS1, where IS1 is that reverse saturation current for Q1, times exponential of VBE. Notice I'm using the same VBE because they still have the same base emitter voltages, the two transistors, and divided by VT, which is again the thermal voltage. So what we can do is we can combine these two equations. So we can think of it, for instance, as we essentially have this same term in both. So you can think of it as solving for one. Maybe we solve for this, we could call this x, for instance. We could solve for x here, and then we could plug it in to our second equation. So if we do that, what we'll see is that we have I naught is equal to Iref times IS2 divided by IS1. And so this is going to be an important equation if we're talking about mismatched transistors. So if we don't neglect base currents, we're going to have another term in there. So for instance, in our general equation for our two transistor current source, we have that 1 plus 2 over beta. In this case, we don't have that because we neglected our base current. So we can see in the limit as these transistors are matched, we have I naught equals Iref. Okay, so we see that our I naught equals Iref times the ratio of some reverse saturation currents. So it's worth keeping in mind that our reverse saturation currents Is are functions of our device geometry. Function of our device geometry and also the electrical parameters. So maybe there's different dopant concentrations, or maybe there's different formations that cause the device to behave slightly differently. So what that means then is that if Q1 and Q2 are not matched, then we have IS1 is not equal to IS2. So of course that's sort of what we're talking about here, not matched, the same as mismatched. So what that means then is that our IS1 is not equal to IS2. And so we can see that is then going to mean that our our I naught is not equal to our Iref. That's what we can see from our red boxed equation above. One thing to mention is that this Is here is a strong function of temperature. So maybe we have our transistors separated a little further. So maybe they have the same geometry, they're just not physically close to one another, and one has gotten really hot. So that could be one reason that we have a mismatched transistor pair. And as we can see, that's going to cause our I out and our I ref to differ a little bit. But this doesn't necessarily have to be a bad thing. We can use this to our advantage because we also know that our IS is a function of our geometry or our cross-sectional area. So function of geometry, as we've already stated above. So what that means then is that we can change the size of our transistors in order to change our I out. So we can change, or we can design size of Q1 and Q2 to adjust our output current compared to our reference current. So basically this becomes a sort of unique design tool. So we have more flexibility because we're not stuck to always having to have our reference current being the same as our output current. And so like I said, we're not going to dive as deep with our MOSFET sources, but if we're talking about a MOSFET current mirror, we have the same idea, and it's actually a little easier to talk about there because we can just adjust the width to length ratio in order to change that reverse saturation current. So here for our BJTs, we're talking in general about adjusting the size of Q1 and Q2, whereas in MOSFETs, we can talk about just adjusting our width to length ratio. So that's all we're going to talk about for this, but you will see some problems in the homework to get some practice and potentially problems on the test as well.